Hi, the SI meteorologist Paul Dorian here with a brief discussion on computer forecast models and overview. Well, in addition to the forecast that we put out here on this website, the siweather.com, the SI organization has been involved with several different forecasting projects over the years. Some of these projects have involved ground truth data collects both in this country as well as other places across the globe for such weather parameters as cloud cover or snow cover or wind speed and direction. Additionally, we have forecasted for a global emergency operations center of a different company with the focus on severe weather to ensure the safety of that company's employees. In all of these cases, the main tool used was the computer forecast model. And we'll talk a little bit about computer forecast models and some of these topics listed here, the background, the basics of them, and how much of a variety of models there exist today, as well as some of the biases that a forecaster has to learn about in order to make some good forecasts. Well, first of all, in terms of the basics of the computer forecast model, all computer forecast models are based on equations that represent the atmosphere. We get into the equations in another video, so we won't get into details on that, but right now let's say there's several different fundamental equations that describe how the atmosphere works, both in terms of a current state as well as a predictive state. These equations are fed in with input data into the computer forecast models, both surface observations as well as upper air observations, and satellite images play a role as well. We also talk about the input data in another video. But the basic idea is once the input data is fed into these equations, the equations are then run and predict the future conditions of temperatures and moistures and other parameters out to as many as 16 days, as we'll see here in some of these medium range forecasts. Now today we have a wide variety of forecast models to choose from. Back about 30 years ago I did my master's thesis work at Penn State with a couple of great meteorologists, Dr. Greg Forbes and Dr. John Kerr, on the main forecast model of the day, which was called the LFM model, Limited Fine Mesh. That was one of about 2 U.S. models about 30 years ago. And the models have improved dramatically over the years. And right now there's several different models that have a different types of data involved in terms of resolution, in terms of the domain, and we'll get a little bit into that over the next few minutes. First of all, I want to put a little emphasis on a couple of computer forecast models that are put out by NCEP, the National Center for Environmental Prediction. The GFS model and the NAM model are basically the 2 major U.S. models right now that a forecaster uses in this part of the world. The GFS model is a global model. That means you can actually produce a GFS model and get some predictions of temperatures and water vapor, etc. in different parts of the world, whereas the NAM model is for the northern hemisphere only, specifically the U.S. and some of the surrounding areas, part of Canada, part of the oceans, and part of Mexico. Now, again, some of these have different time steps. Typically, the GFS and NAM model are run every 6 hours, and the GFS model goes out 16 days, all the way out to 384 hours, whereas the NAM model currently goes out to 84 hours. There are many other models out there now, and many of them are not U.S.-made models or different parts of the world, but they run them for the Northern Hemisphere. So a forecaster in this part of the world can look at the European model, for example. That's represented here by this ECMWF. The United Kingdom has its own model called the UK Met. The CMC is a Canadian model from the Canadian Meteorological Center. NOGAVS and MM5 are more U.S. models, and even Japanese have a model called the JMA for the Japan Meteorological Agency. So again, there are many different models now for a forecaster to choose from, and we'll take a look right now at the NCEP page. Well, this is the NOAA NCEP page where one could go for getting some models, and again they have many different model types listed here. We're focusing here on the GFS and the NAM model, and notice that there are different domains that you can choose for different models. The NAM model will only give you the northern hemisphere, specifically the United States region, whereas the GFS model is a global model, as is the European model and the UK Met model. So all of these models have different domain areas, they have different resolutions, they have different time steps, and the forecaster has to kind of get familiar with each one of these models, and in a moment we'll talk about the biases of these models that a forecaster will learn about over year after year of forecasting with these particular models. Well, once these models are run, they produce predictive information like temperatures and moisture at grid points, and the spacing between the grid points varies from model to model. This is an example of an NAM model, the North American Mesoscale model, one of the main U.S. models, and it happens to be a 12-hour forecast, and some of the output from models include precipitation amounts, temperature, both at the surface and upper parts of the atmosphere. This particular output is a precipitation with sea level pressures around a low pressure system over here in south central Canada. All the colors here represent different precipitation amounts. The darker greens and blues, for example, are heavier, in this case, rainfall amounts, and the black lines here represent equal levels of pressure, in other words, isobars, and the different color lines here represent different temperatures at the surface. So again, these computer forecast models get input data, both surface and upper air data, as well as some input from satellite imagery, and then they crank through all these fundamental equations that describe the atmosphere, and then output at different grid points in graphical display, such as we're seeing here with the NAM model, the prediction for temperatures and moisture and things like that. Well, in terms of biases for the models, a forecaster over the years will learn about some of the biases of the models, and of course all the researchers at NOAA, for example, document some of these biases, and any biases addressed with some tweaks in the model, and that's why models have improved in accuracy over the years. Now here's some of the biases, for example, that are pretty apparent with some of the models that we use frequently. Like GFS model, for example, overdoes light precipitation. This is a trace amount or anything less than 1/10 of an inch. You may see those greens we just saw in that NAM forecast output display. Sometimes it's just overdone with respect to the GFS model. So what a forecaster would like to do is to compare it to other models and consider these biases before making a forecast. GFS has also been known in some cases to have, for example, a southeast bias in the East Coast storm track. A couple of winters ago in February of 2010, where DC and Philadelphia got hit with major snowstorms, maybe 3, 4, 5 days before the event, the GFS may have had the snowstorm, the low pressure system going only so far up the coast, maybe up to, let's say, southeastern Virginia coast. But then as you got closer to the event, the GFS model would forecast that low to go a little bit farther to the north, maybe up to New York City, which of course had all the impact, all the difference in the world in terms of snowfall amounts in Philadelphia, for example. So these kind of biases, again, become evident after a while and are addressed by the researchers in the field. The NAM model once in a while has what's called a convective feedback problem. Actually, it develops sometimes overly convective type precipitation amounts in a non-convective type of event. For example, there may be what looks like thunderstorms with dumping lots of rainfall in a pattern that's more conducive to light to moderate rainfall, such as ahead of a warm front. The European model has often been cited for developing East Coast winter storms just too quickly. It bombs those storms out a little too quickly along the Mid-Atlantic coast, for example, that compared to what actually occurs in reality. So again, the job of forecasters is kind of to learn the biases of these particular models, and of course jobs of researchers is to try to address these, and that in fact has happened. Over the years, computer forecast models have absolutely improved forecasting accuracy. What could be done years ago in terms of accuracy out to 1 to 2 days now can be done out to 3, 4, 5 days compared to a generation ago, thanks in large part to computer forecast models. That's it for now. I'm the SI meteorologist, Paul Dorian.